Hello everyone, this is Proshenjit. So today I am starting with the course. It's a new course in NPTEL platform. Its title is Advanced Manufacturing and Process Modeling. So first of all, I will go through the contents of the course. So we will start with introducing different manufacturing processes, and also we will introduce different numerical methods that we generally use to solve to develop numerical models of these manufacturing processes and to gain insight into them. These are finite difference method, finite value volume method, finite element as well as boundary element method. So we will also discuss about their working principles, merits, demerits and applications, and other contents of the course are divided into 4 different modules. So the module 1 will speak about casting solidification and analogous process modeling aspects. So the content will be introduction to casting processes, different terminologies of the casting process and different functional parts of a typical mold cavity that we use for casting, such as pattern, gate, riser and their design principles and so on. And then we will speak about the die filling analysis. So because it is important to develop a appropriate mold to achieve sound cast parts, and largely depends on the design attributes of the mold cavity, and how to optimize that. For that we will be studying the die filling analysis, where we will discuss the nature of fluid flow, melt flow within the die cavity, effect of back pressure, porosity and air entrapment things. And also we will also look at the fundamental aspects of solidification that is taking place during filling of the liquid melt within the die cavity, and also post filling, that means solidification of the component. And also we will discuss about for both pure metals as well as alloys, and the solidification micro mechanisms for them, nucleation mechanism, different kinds of nucleation, effect of cooling rate on microstructure and properties, and how the microstructure evolves. So we will discuss all these things in this aspect, this sub part of the course. And then followed by that we will be discussing transport phenomena, which is one of the most important and critical part of the casting solidification processes, because it is the melt flow which govern that whether there will be any turbulence caused within the cavity, whether there will be any bubble damage or bubble entrapment or analogous blowhole formation and so on so forth. So we will be studying the transport phenomena of the solidifying melt. We will discuss about governing equations, phase change process, and also finite volume based multiphase multiscale model of solidification. So that example, and we will also discuss about how we can develop solidification model which are truly catering to the different phases, solidifying phases that is evolving within the solidifying melt, and also how we can make it multi-scale, such as simultaneously we can take care of the phenomena which is happening at the macro scale. We can club the microstructural scale phenomena with that. So we will discuss how we can develop multi-phase and multi-scale model. And then we will also discuss the initial and boundary conditions of a typical finite volume model of solidification transport phenomena, and afterwards we will discuss about the coupling of the CFD based solidification model with the phase field model, wherefrom we can also simulate microstructure formation of the solidifying parts, and also we can predict the different kind of defects those generally gets generated during solidification. And once we are done with the casting module, we will move to the second module of the course, which deals about with welding processes and analogous process modeling aspects. So in this module we will discuss about the different kind of welding processes, different kind of joints, classification of welding processes, insight of weld metallurgy, weld mechanics, weld defects, and also we will discuss about how we can alleviate the defect formation, or we can minimize the defect formation tendency during welding assisted solidification process. And then we will also discuss the analytical and boundary element method to solve the heat conduction equation applied to welding processes. And then we will discuss finite volume, finite element based formulation, multi-phase flow model of melt pool transport phenomena and solidification in fusion welding processes, and followed by thermomechanical modeling of the residual stress evolves during welding. So these are the different contents of the welding module of the course. So here also we will borrow the knowledge what we will be gaining while discussing on the casting module, and we will see how we can predict microstructure evolution during weld joint solidification. So while moving with the course, we will reach module 3. So that is the powder metallurgy and process modeling. So powder metallurgy is important, is a typical net shape process where we can basically develop parts which are otherwise very difficult to manufacture by other conventional manufacturing techniques. So here we will discuss about we will introduce the powder metallurgical processes and their applications, and then followed by powder preparation techniques, mechanics of solid state sintering, hot isostatic pressing, and then some advanced powder metallurgy processes like injection molding, powder forging, powder rolling and extrusion for both metal as well as ceramic powders. And then again we will discuss about the importance of numerical modeling of transport phenomena involved in injection molding, more specifically polymer or metal or ceramic injection molding processes. So so here the goal will be the estimation of filling and cooling time, injection pressure, defect generation, and also followed by we will discuss finite element based continuum model of sintering densification and mechanical behavior. And also we will discuss about the molecular dynamics based model of neck growth during sintering, and also microstructure evolution. So here one thing is important. So here the goal of developing these numerical models is twofold. Number one, that it is important to learn those to optimize the processes, so that we can optimize the process conditions to get the desired quality characteristic, and also to investigate the physics involved in the process. So with this two-fourth goal, we will develop the discuss how to develop the numerical model for powder metallurgy processes, and then we will discuss about different additive manufacturing processes which are presently being used worldwide, and also we will discuss the importance of developing accurate and appropriate numerical models based on finite element and finite volume route to model additive manufacturing processes. So we will discuss melting solidification, heat and mass transfer aspects, followed by microstructure evolution models in case of multi-layer and multi-track additive manufacturing processes. And then we will enter into the last and final module of the course, which speaks about metal forming and process modeling. So here we will introduce different forming techniques like forging, rolling, extrusion, wire and tube drawing, hot and cold working, etc. And also we will discuss about different analysis techniques of metal forming processes, which include slab analysis of rolling process, slip line analysis of punching, as well as experimental methods to assess formability of sheet materials. And then we will discuss forming limit diagrams, and also along with this the fundamental theoretical aspects of metal forming. We will be discussing how we can develop finite element based process models to study deformation behavior of different metals which are subjected to metal forming. And also, as I told you earlier, this these numerical models will also prove to be immensely helpful to optimize the conditions where we can get the accurate flow behavior of the plasticifying metal. Because appropriate control of the process conditions can can result in better plastic flow of the metal, and which can result in sound structural integrity in the developed formed forged parts. So and then we will also discuss about how to develop finite element models for different metal forming processes such as forging, rolling, drawing and shearing, and we will also compare the FE formulation with the analytical techniques. And then at the end of the course we will discuss about different machining processes, and also we will discuss about how we can develop finite element model of chip formation in case of orthogonal machining, in case of oblique machining, and also we will we will also discuss how we can develop process models which can club the macroscopic model, FE model with the capability of predicting chip microstructure. We will also discuss about the FE model to investigate the chip size distribution and also the cutting forces, judging machinability of light alloys composites. So, these are the basically the content of the course, and these are some of the reference books that is highlighted in your screen. So, you can see that here there are books which are encompassing from the fundamentals of the manufacturing processes which are going to be covered in this course, and also there are books which speaks about different numerical methods. And so for example, J.N. Reddy, for example, H.K. Versteeg of computational fluid dynamics and finite element method by J.N. Reddy. So, along with the other fundamental books on manufacturing technology by P.N. Rao, Ghosh Mollik, etc. So, if you follow these books, then it will be quite effective for you to learn from this course, and also going through the fundamentals and to grasp the knowledge that I will try my best to impart. So, with this I would like to finish this introductory session of the course, and we will start with the first lecture for the course. Thank you.